the objective that we're going for is to determine the stresses inside a beam when it's being loaded. And this being under pure bending, it probably won't happen exactly like this, but we do it this way in order to develop equations to be able to make it easier to solve future problems. And even within this problem of pure bending, we need to develop certain primary principles in order to have the tools to develop further more easy to use equations when we're trying to solve for stresses. And there's three developments that I want to go through. I kind of just break it down this way because it makes it easier for me personally to be able to remember things in sort of the conceptual blocks. Rather than trying to remember everything at once, I try to break it up into parts and groups. And you may find this helpful. So anyway, the first thing that we need to develop is a relationship between the distance y, which is the distance from the neutral axis to whatever point you want your stress. And the cross section is going to be a piece that looks like this. So your distance y is going to be from here to some point here, or even up. Doesn't really matter. You choose any point. And so that's the distance y that we're talking about. It's the distance from the neutral axis. And it's going to be the distance from the neutral axis versus the deformation. And the deformation designated by a symbol here. And so in order to develop that relationship, we need to first recognize, because we're basically working with this idea that deformation is the original length plus or minus the length after the load is applied. And so like we saw, the length at the top of the beam is going to be shorter than the original length, and the length at the bottom of the beam is going to be longer than the original length. In our case, we're going to use the length at the bottom of the beam. We'll call this L prime. It could be any point in here, and but it just can't be 0. And so what we have is the length at the neutral axis is going to equal theta times the radius of curvature, and we get that just from the definition of arc length. You usually see it in the form S equals R theta or something like that. And so now we have our length in terms of theta and the radius of curvature, and now we have our L prime, which is our deformed length. And so our deformed length, L prime, is going to equal theta, because the angle is going to be the same, times the radius of curvature, which is the distance from the center of the circle to the neutral axis at the end of your beam, and then plus some distance from that center, wherever you're looking for your stress. I've drawn this to show that it's basically at y max, the maximum, or y min, or furthest down from the center that you can get. And so R of k is going to be this length. Then if we're going all the way to the edge of the beam, it's going to be plus y. And so we have R of k plus y is going to be our new, basically our new radius for the arc. And now our equation is going to look a little bit better. We have our deformation equals the change in length. And so if we make a few substitutions, we see that the change in length equals theta times the radius of curvature minus theta times the radius of curvature plus y. And do a little algebra here, and everything cancels out except negative theta y. So our change in length is related to the angle that our arc sweeps out times our distance from the neutral axis. And you'll just see, so basically we can say that the deformation is proportional to the distance from the neutral axis. And so if y is 0, the deformation is 0. This just confirms what we were talking about earlier.